to record this. Let's see. All right, cool. Then yeah, at least thanks for you two showing up and for showing an interest in uncertainty. So did you guys attend the lecture? The lectures? Okay, yeah. All right, so maybe just like super quick recap. And did you attend last week's tutorial? Yeah, okay, cool. So I mean, there's your classic Bayesian inference problem, right? Like what we want is a distribution. So for a test sample, X star, Y star, what we want is a distribution over that prediction or some kind of measure of uncertainty, right? Ideally in a Bayesian setting, you get a full distribution. And in the Bayesian framework, what you do then, right, is like, this is called the posterior predictive distribution. And then the Bayesian framework, right, you can kind of factorize or express it as an integral where you have the probability of y dependent on a specific weight times the posterior, right? So this is the classic Bayesian posterior, which is just the distribution of weights given your training data. And then you integrate over the weight space. And now the problem is like, okay, this you can compute, this is just a likelihood. And then you have your posterior. And like in the classic Bayesian framework, right, in the classic Bayesian framework, the posterior then is expressed as the likelihood times the prior divided by the evidence. And so again, the likelihood, if you make some kind of distributional assumptions like, oh, it's a Gaussian factorization or something, this is computable. The prior is obviously something you impose. It's an assumption you make. So again, if you say this is some kind of Gaussian, and in this case also factorizes, you can also compute that in closed form. And then you have the evidence, right? And the evidence is the problem because the evidence is essentially what you have on top, but just integrated over the whole support of the weights. And so even if you assume if you say, for example, your weights come from a Gaussian 0, 1, like a standard normal, right? And the weights still have support on the whole real line. And so basically this integral would be integrating over the space of real numbers. So it's impossible to compute this integral. And so what we do in kind of Bayesian inference in general, and perhaps what you also saw last week is like, we try to find ways to kind of go around fixing this. And essentially we try to find ways to compute this posterior with some kind of approximation using samples or using other assumptions. And I think last week you saw like the Bayesian neural network where you trained it using stochastic variational inference, which essentially means that you approximate this with some approximate posterior Q, right, which is based on some kind of assumptions, typically some Gaussian assumptions. And then you try to compute the parameters of that approximation using what you call the elbow, the evidence lower bound, which is like this derivation. So yeah, but we're not be going that, but like kind of that's the recap here. And so now in the same setting with the uncertainty methods that we look at today, it's like, okay, how can we kind of go around, right, not having this readily available? Can we find ways to kind of approximate it or do something else? And so, yeah, last week you saw essentially just variational inference, like the classic Bayesian methods are Monte Carlo sampling and variational inference. And today we'll be looking at things that are perhaps a little bit less Bayesian in that sense, but a bit more practical. And so that's something that you could actually perhaps use in more settings, and that has been empirically quite successful. And so specifically, we'll look at deep ensembles, we'll look at Monte Carlo dropout, and we'll look at somewhat unrelated, but well, related to my research, which is why it's included, is conformal prediction. So yeah. So maybe I mean, do you have a general idea of what ensembling and Monte Carlo dropout are? Or, I mean, okay, I'll go over it. I think we'll just, yeah, go along with the notebook and see where it comes and how they relate to each other. So I'll just start by importing my stuff. So in this case, So we first have kind of a tutorial example using this toy data set, which is basically just kind of to understand the methods, what the intuition is. And then we had the actual exercise where essentially now we're going from regression to classification on MNIST. And we also try to kind of quantify uncertainty on MNIST predictions. Did you have a look at the tutorial or no? Okay. I mean, how do you guys want to do it, for example, for the exercise? Do you prefer to... So we'll go through the first part together, obviously, and then for the second part, do you want to kind of try stuff on your own, or should it just be rather kind of showing the methods, or shall I give you some time to think, or more just like open questions type?
It's fine, going through it.
Yeah? Yeah. Okay. I mean, yeah, just asking. All right, so let's start with the first one maybe. So here we have this 1D example. I'll just run the data. So what do we have here, right? We have some kind of true function, which is shown in blue. And this true function consists of some kind of combination of sinal waves with some kind of shift. And then we sample from two specific sections of the support of this function, which is where we have these black dots. And in particular, we sample them and we add some noise here. So we sample from these two subspaces here, and then we add some noise to represent kind of noisy real world examples. And yeah, this is our original function here. So we can plot this. So my first question would be, why do you think this is, for example, a good example to visualize uncertainty? Or kind of what's the intuition? Like, for example, why don't I have blacks? Like, why don't I just sample black dots everywhere on the whole support?
Because often in a real life situation, you don't have the data for each.
Yeah, fair enough. Okay. Okay, let me ask it this way. If I use some kind of uncertainty quantification methods, you know, using a neural network trained on the black dots, right, on the observations, do you have some kind of intuition of how the neural network would behave in the areas where we don't have data?
It would act as if it knows something that in reality, like based on data, you only have two regions, what's happening, and the rest is unknown, basically.
So it would just be interpolating, right?
Yeah.
Okay, and so now if we add some uncertainty quantification method, do you have an intuition of how the uncertainty would behave if we... Okay. All right, good. Yeah. That's about right. Yeah. And so in particular, kind of the uncertainty that you quantify with Bayesian methods and also these methods is, I don't know if you had this distinction between aleatoric and epistemic uncertainty. Okay. All right, never mind. So, I mean, in essence, there's two types of uncertainties, and all these methods we look at, also Bayesian methods in general, they quantify one source of uncertainty, which is the uncertainty you have in your model prediction and in your weights and your parameters. But yeah, so that you would expect that to be high in these areas because, well, your model is essentially very unsure of what's happening here because it has never seen any training data in that domain. So we'll see if this actually happens. So we'll start with just like a regular, this is our model, right? Our model is just a 3-layer MLP, classic fully connected neural network. So we have one input layer, one output layer, and one hidden layer, at least in this definition here. And we use, so we have this Boolean flag to specify if we want to use dropout or not, because we need that for one of the uncertainty methods later. And we use tanh nonlinear activations. And we actually add a residual connection in here to skip the hidden layer, which normally I wouldn't do if you have the only 3 layers, because like you would only use that typically for like very deep networks to help the gradient flow. So, but yeah, they added it here. So, yeah, and then we'll define our training loop, right? We just cycle through our data points here. We optimize using Adam optimizer and the mean squared error loss. And so let's just train it on the black dots, right? The observations that we have. So in particular, we have 3,000 samples. All right. And now we can plot the predictions. And so, yeah, I mean, we can see that it, fits nicely to wherever, right? It's seen the data, and then in domains where it hasn't seen any data, it just kind of interpolates. And I mean, it's pretty far off the original true function. So now we'll start with kind of quantifying the uncertainty around. I mean, this is what we got, right? We got to work with this network, and now we just want to see, okay, right? If I was somebody and now I would ask for a prediction here, and you would give me this, right? And what can I do with it, right? Like, okay, it's pretty far off the true line. I don't know the true line, right? But then, right, should I trust this prediction, right? I don't know. It's just a prediction. And if I had the ground truth, I'd see that this would be a pretty bad prediction. And so the hope is now if we add uncertainty, right, then you can give me this prediction, but you can also say, oh, by the way, my model was super unsure about this prediction. And now I can, I have more information. I can say, okay, well, can I really trust this or not, right? I have more options. So the first thing we do is deep ensembles. And the idea is super naive. It's like ensembling to improve performance, right? That has been done since like the 1970s, like statistical bootstrapping and things like that, right? You just take a bunch of models, you get the predictions, and then you do some kind of summarization over their predictions, like a mean, or I don't know, you can do a mode, whatever. And now in this paper, it's like, okay, well, why don't we also encode the disagreement between the models or the variation between the models as a measure of uncertainty? And so the idea is like, okay, instead of only taking the mean over the models, you could also look at the variance of predictions and use that as a measure of uncertainty. Or you could look, like we do later in the example, you can look at the entropy, which is also a measure of kind of dispersion. And yeah, that's about it. Like if you take a bunch of models, right, you run the predictions, and then you just use an additional measure of, you encode some kind of variation as a measure of uncertainty. And now, obviously, people are like, okay, this is too simple. Like, we need some kind of theory behind it. So people try to motivate it, or papers try to motivate it as a approximate Bayesian inference approach. And so what do is they say, okay, well, we have this posterior here, right? It's intractable. So what we do is we approximate it by some posterior Q based on parameters theta. And in variational inference, right, you then had some distributional assumptions on that form. And in this case, with ensembling, you say like, okay, this approximate posterior is in fact just kind of approximated by a sum of Dirac deltas. Now, what does that mean? So it means that if I have 5 neural networks, each of these networks is trained, it will be trained a little bit differently. And so you'd have 5 kind of different versions of weights, right? So you have 5 different kind of sets of weights. And now the motivation is, okay, each set of these weights, theta I, can be interpreted as a mode of the posterior, right? So a high probability region of the posterior, because, well, we train the 5 networks. These are the 5 sets of weights we get. So we consider those high probability modes of the posterior over weights. So we'd say that, okay, given on these 5 samples that we have, right, we consider these as actually kind of, right, occurring. And then you just say, okay, well, each of these is a Dirac delta in the sense that it means it just has support only in a single point, which is the mode, and otherwise it doesn't, right? And then, yeah, that's it. You say, okay, I approximate my intractable posterior with an approximate posterior, and my approximate posterior is in fact just a series of individual points, which I consider to be in high probability regions of my true posterior. And yeah, I mean, this argumentation is debated in the literature, because you could say like, okay, I have a super rich true posterior over a whole, I don't know, big domain. And now if I take an ensemble of, I don't know, 5 or 10 networks, I'm approximating this huge distribution with 5 or 10 individual points, right? Like how good can that be? But in fact, what happens is in practice, this method works pretty well. And so the theory only followed after, but it's kind of, yeah, it's like a motivation more than like a real theory in that sense. But yeah, that's how they motivated. And so this is based on this paper. This is the original paper that suggested this the first time. And I guess one thing kind of that they highlight that's important is that obviously if you want to cover as much of your true posterior with these points in the modes, you want the modes to be very diverse. So you want each network to kind of explore a different area. And so what they say is like, okay, you need some kind of diversity in your networks. And so there's a lot of literature about like, how do you train multiple ensemble members and make them kind of diverse? There's like different objectives that you can use and things like that. But in the original paper, all they do is set different random seeds, and that's like it's already works. So yeah, in this case, we look at 5 ensemble members, right? And now each of them has 2 layers, I guess. And now we train the 5 members here. And then we essentially collect their predictions, right? And plot their variance, or standard deviation rather, in the later parts. So here we just plot the 5 networks that we train. All right. And then for each of them, we collect the predictions. And then here we just plot the 5 networks, right? So you see that kind of, I don't know how, diverse they are, but you can see like the 5 networks, they do differ a little bit, at least in their predictions, especially in the regions of no data, right? Because they interpolate differently. Yeah, this is what I was saying here, right? So in practice, right, you approximate this posterior using this Q posterior, and each of them is just these individual weights of each network, right? And so here we can now just quantify the uncertainty using the standard deviation over predictions, right? And now what you get obviously is just essentially this here expressed as an interval, right? Where now you essentially have these prediction bands. And so you would say, okay, whenever the models disagree a lot, right? That's where kind of you're lacking data or information, because the models seem to think very different things. And then in regions of kind of a lot of data, right? Obviously, the models agree very closely with each other, and so you have very low uncertainty. Yeah, so this is kind of a very simple, naive approach to approximate, motivate a Bayesian approximation, and it works quite well in practice, actually. But it comes obviously at the cost of having to train multiple models and kind of running inference with all of them. And so one alternative way. So in the classification task, so we'll actually see that later. So in the classification task, you can do the same kind of using the softmaxes. So you could collect the 5 different softmaxes, right? And then you, for example, just average over them. And yeah. But the way we do it here is to quantify the uncertainty over the softmaxes using entropy, which is kind of a more suitable for classification than like a standard deviation or something. But I'll show it in a sec. Okay, so the motivation for Monte Carlo dropout, like it's this very similar idea, right? Again, you have your intractable posterior, you approximate it with this tractable posterior, but then again, you just say, okay, this one I approximate using these individual dots, but now these individual dots don't come from different neural networks that I train, they come from different versions of the same network using dropout. And so what is the idea here, right? The idea is normally dropout is used during training to regularize the network to not overfit to the data, because you kind of like drop out specific sections, specific nodes of your network, right? And then basically you try to promote kind of different connections in the training process. And so then the whole idea of Monte Carlo dropout is like, okay, why don't we just use dropout during test time? And so what we just do, right, is because normally in a dropout network, you don't regularize at test time, right? At test time, you use all the information you have available. And so here you would say, okay, I also want to generate these kind of different samples. How do I do that? I do that using dropout at test time, because at test time, right, I can take a network, I can drop out a bunch of the nodes, and I can run the prediction through it. And now I can take the same network, I can drop out a different set of nodes, and I can run the prediction through it. And because different nodes will be dropped out, right, the predictions will differ, because essentially the information gets channeled through different, is encoded through different channels. And so in a way, this is the same as doing ensembling using the same network, just where the ensemble members are generated through multiple forward passes with different dropouts, right? So you say in the first version, I drop out, I don't know, the left node. And then the second version, I drop out the medium node. The third version, I drop out the third node. And so then you have these different predictions, right? And you can consider them as an ensemble. And then you can do the same thing, right? You can compute their mean and their variance, and you can quantify the uncertainty. And so that's exactly what we're going to do here. So here we train a single network, but now we use dropout. So it's important to use dropout both at training and at testing for this kind of method to work. Again, like, and this is based on this paper here, which was super, so it got super popular. It's from 2016. And yeah, I mean, they have here their motivation, right? The theory, and essentially you see what we have here, which is the posterior and the Bayesian approximation. And all right, so let's run this. So we'll do 100 samples. So now the beauty of using dropout is you don't have to train multiple networks, right? You just have to do inference multiple times. And so instead of having only 5 ensemble members, here we can actually run 100, for example, and it's much cheaper, right? So here we just run 100 kind of inference steps using different dropout masks, and then we visualize the predictions. All right, we see there's like a bunch of noise, and they all differ, so they're all kind of overlaid on top of each other, right? But there's essentially 100 different predictions encoded in here.
So you like dropout, when you train dropout, like during inference, you not only sit on your multitude federate, you also turn off dropout manually.
So if you just use it for regularizing during test time, you don't use dropout.
Okay, but you turn it off manually, basically.
Sorry?
I assume that like in Torch,
yeah,
when you basically set your model to the prediction mode,
yeah,
you also turn off dropout.
yeah, exactly. Yeah, so here you have to, so you should set it to training mode. Yeah, exactly. So if you set model.eval, then it will, yeah. So yeah, you set it to training mode. Yeah, exactly, yeah. Yeah, and so here, obviously, now the uncertainty is just quantified by the variation in these 100 test time predictions. And so similarly, right, you get now like a prediction band. And again, you see like uncertainties higher in areas of low, kind of with no data, because that's where the models are most unsure of, where they disagree the most. But I mean, even if you compare these two already, you see that ensembling seems to do a little bit better than this one, at least in our specific use case. And I think probably mainly because for this toy example with like a 3-layer network, it probably doesn't make sense to regularize with dropout. especially because the dropout we use is, I think, 50% dropout, which means that, yeah, that's a lot, right? So then we'll lose a lot of nodes in our small network.
So the kind of the upside of using ensembling methods, using dropout instead of sort of training different models would be mostly in the performance-based improvement. You can run more predictions because it seems like it's actually less effective at capturing the real uncertainty than the other one.
Yeah, so I mean, those two are like the two. So they came out 2016, 2017. So and surprisingly, they've been popular up to now. So in a sense, like there's not much else that does particularly better. Just maybe because it's just a really hard problem to start with. But yeah, I would say the main benefit is in computational cost saving. Yeah, in terms of performance, it depends. Sometimes one does better, sometimes the other does better. I mean, there's a lot of new options. For example, for ensembling, I don't know if you saw in the lecture as well.
What would they, like, assume that you have basically unlimited computation? Would you use dropout or would you?
I would use ensembling, yeah.
Okay.
I would use ensembling.
Because of being able to test with different architectures.
Yeah, exactly. So the crazy thing is ensembling was so popular that people started ensembling over everything.
Yeah.
So people started ensembling over different model architectures. People started using the same model and you just ensemble over different parameter configurations. People started ensembling over batch normalization in the same way like you can do it with dropout, right? You can also do it with batch normalization. There's like a different people started like during training, you make kind of in between snapshots of your weights and you ensemble over those. So like it's like it's gotten really creative. So yeah, you'll find a lot of different ways to ensemble. And so I think so it's still kind of one of the best ways to use it. But then it depends on your specific use case, kind of what type of ensembling you want to do. And I think what makes it so popular as well is because it's just so simple conceptually. Yeah.
Yeah, but also like as you mentioned, that maybe dropout is suitable for a autoencoded architecture.
Yeah, exactly. So yeah, I mean, dropout to regularize, like it's also fallen a bit out of fashion. So now people tend to use more like batch normalization, things like that. So yeah, there's a paper that does the same idea with batch normalization, but it didn't pick off quite as much as this one. Yeah. Okay, and then yeah, the last thing, which is kind of like slightly random perhaps, but is conformal prediction. And so conformal prediction is not anything Bayesian related at all. Actually, it's based on frequentist statistics. And kind of why we include it here is because it's been really popular in the last 2 years or so. It started being really popular as just a method to quantify uncertainty, like regardless of Bayesian, non-Bayesian, whatever, right? Is it model uncertainty, other uncertainty? It just focuses on predictions and uncertainty of predictions. And it does it in a really like elegant kind of statistical based way. And so, yeah, I guess kind of the key components are quite simple. It's like instead of just using training and test data, we have an additional data split, which we call the calibration data. And now on this calibration data, we try to basically extract as much information from it as we can to use for any future test predictions. And how do we do that? We use what are so-called, did I mention it here? So-called conformity scores, which measure kind of some kind of agreement between the ground truth, so the real values, and your predictions on this calibration data. So in the most simple case, you could imagine just like the deviation between your prediction and your ground truth, so like the absolute residual, right? So you just say, okay, I predict 0.5, my ground truth is 0.3, right? So then that score would be just be 0.2, like the difference in the most naive method. But so there's different ways to design these scores. And then you order these scores, you say like, oh, from smallest to highest, and then you take a specific quantile. So you say, I'll take the 90th score, the largest score. And that would be this conformal empirical quantile Q hat here. And then all you need to do for any future test prediction, you predict using a single model, and then you can build a prediction interval around that model using this Q hat. For example, by just doing plus Q hat minus Q hat. And then you have a prediction interval. And now you could say like, okay, sure. I mean, there's different ways to build prediction intervals, right? You can use like normal Gaussian assumptions. You could do bootstrapping, whatever. Like prediction intervals have been there since like the 1930s. But what's really nice about this method is, first of all, it's purely empirical. So it doesn't make any assumptions on the distribution. So your data could be distributed whatever way you want, right? This method will still work. And the really, really nice property is that if you follow this whole kind of conformal recipe and kind of do your computations, you get this statement here. And this statement, right, even if it's very small and short, it's really powerful. Because essentially what this says is that I can guarantee you, I can promise you with a probability larger than 1 minus alpha, where alpha you pick it at the beginning. So for example, 0.1, and this will be 90%. So I can promise you with 90% for any future prediction that you make, if I construct my conformal prediction interval, the real value will be inside that interval. Right? So again, I can promise you for every future prediction that the real value will be inside my interval. And so like this is super powerful because essentially you can give a guarantee on the ground truth. So on a value that you don't know in the future. And you can say, okay, I give you this prediction interval and I can guarantee you with 90% that the ground truth will be in there. And so now you might think like, okay, this sounds maybe a bit too nice. And it is because this probability here is marginal. So this is a marginal coverage guarantee. So coverage guarantee, excellent. Marginal, not excellent. So what this means is essentially this probability, it holds on average over all your future test data. And so that means like if you give me 100 test points, right, then I can guarantee you on average over 1 million test points that this will hold. But for the specific 100 test points you give me, maybe, right, maybe this statement will not hold. Maybe it will be like 20% or 30% coverage. So, right, in practice, kind of, maybe this is like, right, this cannot, it can be not useful in practice. But from a theoretical standpoint, this is amazing, right? So like, oh, all these ensembling methods, whatever, right? Sure, I can give you an interval, but I don't have any theory to guarantee you anything, right? But here you have an actual statement and probability. So yeah, if you like theory, you should get excited about this. And so yeah, in this simple example, we can play together. I'm not gonna like go into all the details and stuff because yeah, like if you're interested, there's a really nice introductory paper to this topic. And yeah, it's been getting a lot of attention recently because people realized, oh, right, if we want, so we not only want uncertainty, but we also want some kind of theory statements behind it, right? It's really nice to have some kind of trust in our uncertainty. So not only in our, so it's like, oh, you give me a point prediction, right? I want trust in my point prediction using an uncertainty interval. And now we go a step further and now we say, okay, well, I also want to trust my uncertainty. How do I do that? Well, there's no ground truth uncertainty, right? I mean, we don't know. So the best way to basically trust your uncertainty now is to have some kind of theory guarantees. And so this is one of them. So yeah, so we can do that here, right? So now we take our data, we split it into training and calibration data. So I just take 20% of the data for this calibration. I train my one neural network. And then I run my predictions. And so now I just visualize my predictions. So here I didn't do anything with conformal, right? This is just the neural network trained on 80% of the samples. And so, okay, you know, it looks similar to the one trained on 100% of samples. So it's fine. So now comes the conformal part, right? So in this case, I'm looking at just the residuals, which is what I was motivating before. So I compute the residuals, then I compute the conformal quantile. Again, all of this is, another beauty of this approach is it's all super simple, right? These are like 5 lines of code, like, and it's, you know, there's no approximations, nothing, right? It's literally just like some basic manipulations, right? So I compute my residuals, those are my scores. Then I take Q hat as the 1 minus alpha quantile of these scores. So I choose alpha 0.1, so my guarantee will be for 90%. And now I just build an interval where I take the prediction and I do minus Q plus Q. All right, so we can visualize this. And then we get something like this. And now you might say like, okay, that looks kind of crap because like it's actually not big where there is no data, right? And I'll tell you, yeah, that's right. But this is because we use these really, really basic scores here, right? So these scores, I mean, there's no notion of uncertainty in these scores, right? So it's always a fixed value. So obviously, right, we will always have kind of a fixed size interval. And so I just chose this because this is the simplest case, but in a more sophisticated setting, you would kind of use a different type of score. And you might, for example, even include some measure of uncertainty like a sigma, and then this would actually be adaptive. But in our case, right, all we do is take a fixed value and basically create an envelope around our prediction. And now you might say, well, okay, this actually doesn't really look like it will cover 100%. And you're right. So it covers like 50%. So I would say in this case, right, using this specific score sucks. But what's really nice to see is now you can really see the statement I made before that this is a marginal guarantee, right? So if we check the coverage on only the regions where we actually have data, right, we're at 100%. So this is actually more than we want. So, and then the regions where we don't have data, we're at the 50%, right? Because we're obviously way off. And so this is kind of the statement I made. It's like, okay, on average, the guarantee holds. I mean, in this specific case, not because, well, the ratios don't match, right? If you take the average, it would be 75. But kind of like in the long term, right, you would get the 90%. And so what is the problem here? Obviously, the problem is one, that we're using this kind of fixed size. And secondly, also is that there are some assumptions on kind of the distribution similarity in this setup. Not on the shape of the distribution, that's really important, but on the similarity. All right. That was the theory part. Is there any questions? Otherwise, that would we go into the exercise for classification on MNIST? Yeah, 5-minute break? Yeah, cool. Yeah, I mean, stop me if you have any questions or comments or anything, right? Let me pause this. All right. All right, welcome back. So now we had a look at deep ensembles, Monte Carlo dropout, and conformal prediction on the one-dimensional regression toy example. So now in the exercise, we'll try to look at them for MNIST classification, and specifically we'll use them for distribution shift detection. And so perhaps in a way, it's a bit similar to your project on outlier detection, in that we'll try to see if these methods are kind of able to react to distribution shifts. And so what we're going to do, in fact, is we're going to take MNIST images and we're going to start rotating them slowly. And we'll increase the rotation angle. And then we'll try to measure the uncertainty using what we show here using entropy. And so why would entropy be suitable in this case? Because it's kind of like taking or quantifying uncertainty using, right, some kind of measure of dispersion in general. And I don't know, using like a standard deviation over softmaxes is like a bit meh. So kind of using entropy as a measure is an entropy measure is kind of the distribution of scores. And so in our case, in MNIST, you have 10 different digits. So you have 10 softmax probabilities that your model outputs. And so if your model is kind of very uncertain, right, you would expect essentially the softmax scores to be very widely dispersed among the 10 classes, which would result in a high entropy. On the other hand, if your model is super certain, right, it'll give 99% softmax probability to one class. And in that case, right, your entropy will be very, very small. I mean, you can check this just based on the formula. And so, yeah, so we'll use entropy, and essentially we will start rotating MNIST digits, and we will have our model predict the rotated images at different rotation angles, and we'll measure the entropy or the uncertainty as measured by entropy. And so we'll just, first I'll do the whole setup here, so just bear with me. All right, so here, for example, downloaded MNIST dataset. Now here you can see an example. We have an MNIST digit here, right? So 5. And now we rotated it by 90 degrees, right? So now it's just a squiggly line. And so obviously the model is only trained on the original images, not on the rotations, right? And so then doing testing, we start rotating the images and we have the model predict them. We would, right, expect some kind of something to happen, which I'll ask you in a bit what's going to happen. So first we do the split, right? So we train and test data. It's already split up originally. And now we define our MLP, and now we train it on the original MNIST. And because it's a classification task now, we use cross entropy loss, like the default classification loss. And we train it using Adam again. And no dropout, no nothing. This is just your original. Oh. Okay, and then the nice thing about MNIST is like, yeah, 70K images. And this is like a super small neural network, so it goes really quickly. So we literally just train the network. All right, then we can define our scores, right? So we can define the accuracy. So how many correct labels do we get? And now we can run this for our deterministic model, right? So we just train the model quickly, and we actually get 92% accuracy on the unrotated images. So we just train the model now on 50K MNIST images, and we predict on the other 20K, and we get 92% accuracy in label prediction, so the correct digit prediction, which is pretty good. I mean, obviously, right, state of the art for MNIST is like 99.8 or something. So in that case, like this is not good, but you know, for our purpose, this is quite good. Okay, now we can start rotating images. I mean, this is just kind of manipulation stuff. So I'm not going to bore you with it, but essentially we take 100 test images and then we start rotating them at any angle between 0 and 90 in 3% increments. So let me maybe show you this. Right, so we have essentially all the different rotation angles between 0 and 90%, and we rotated by 3 degrees each. And now what we do, right, is like we have our network and we let it predict on the images, and then we pass it through softmax. I mean, you could also use different stuff, but right, the classic is to use softmax, and we collect these for each of these rotations. Right, and then here there's a little description about the entropy, right? So the uncertainty The more uncertain, right, the higher the entropy. That's what I meant. Like the probability, it measures kind of dispersion of probability mass. So if your probability mass is more distributed among the 10 MNIST classes, right, your model is more uncertain, you'll record higher entropy. Okay, so the first question would be like, how do you expect entropy to behave as you increase rotation angle? Yeah, not a surprise. I mean, ideally, yeah, exactly. Ideally, right? The more you rotate the images, the more the distribution shift is between what it has seen in training and your test data. Although it may not be true for all of them, like for example, like an 8, right? Yeah. It's kind of like, but then we only rotate 90 degrees, so I guess it still works. But yeah, exactly. So the distribution shift would increase, and then you would expect your model to be like, oh, I'm more and more unsure what's happening here, and you'd expect your entropy to increase as well. So the first thing is we implement the entropy here. So I will not have you implemented, but I will just keep it in here so I can do this. And then I'll run the implementation of the entropy here. So this is wherever there was like not implemented, this is where you guys were supposed to do something. Yeah, okay, got it. Exactly. So we can compute the entropy, right? We just follow the formula up here. And now we can run this thing, right? So we can calculate the accuracy, calculate the entropy, and plot it. No, I'm giving it away. All right. So what do you conclude just from this plot?
That 45, at least the entropy stays.
Yeah. So this is a model. There is no uncertainty quantification here. This is just our regular model. So would you conclude that, I don't know, is the model robust to distribution shift? Okay. And yeah, and interestingly, it's true that after a given rotation angle, right, kind of the entropy stabilizes in the sense that you could almost say that the model has reached, in a sense, maximum uncertainty. And so it will not, right, it will just stay at that uncertainty level. I mean, we'll see that in the later. This is just general entropy. I mean, here, essentially, uncertainty is measured just with the softmax. All right. So now we'll do the other stuff we have, right? So the Monte Carlo dropout. Again, now we need to adapt it to MNIST, right? So MNIST are 28 by 28 images. So we have 780 input channels, 10 softmax classes. So we have 10 output channels, and then we add 3 intermediate layers. Obviously, again, for dropout, to use dropout at test time, we also need to have it at training time. So now we train our network with dropout on MNIST. And we would expect kind of a similar accuracy, just generally. Right. Let's see, 92. Okay, close enough. All right, and so now kind of the task would be, okay, implement essentially dropout with 100 samples for this task, right, for MNIST. So I'm not gonna live code because it always tends to get messy. But I will paste the solution. And so what do we do here, right? Now for each of the images, right, we run it. I mean, we collect the predictions, obviously, and then we run it through our dropout loop, right? So we have 100 dropout samples. And again, here, I think this is what you were asking, right?
Yeah.
Like, yeah, make sure to set it in training mode so that dropout is activated. And then so we loop it through these dropout masks 100 times, right? For each image, right? We run it through the 100 samples and we collect the predictions. And now the question here is, how should you average the dropout predictions? For example, should you collect all the logits and then average them and then run it through the softmax, or should you collect the softmaxes and then average them?
Collect logits. Whereas your
mathematically are they the same? Or no?
No, no, they'll be different.
If you use the softmax, you already run an operated value, right? But like it is terms of what you want to depends on what you want to do.
No, but I think you're
simplifying it already.
Yeah, exactly. So I mean, the softmax, all it does is kind of like take your logit and squish it into some like interpretability sense, right? Into like your probability space. So taking different probabilities and then averaging them is a bit weird. So you're right in that we take the logits and then and so then we can run our dropout network. And so now, how would you interpret this plot now? So now we plot the one just based on original kind of predictions, and then now the one where we added kind of dropout. So obviously both of the underlying networks, right, fail in the sense that they, right, their test accuracy reduces with rotation angle. But how do you interpret kind of the difference in entropy here?
About has more uncertainty.
Yeah. I mean, it does. It has a similar behavior, right? Like similar curve, but it's a bit shifted. And so, I mean, if we want to quantify uncertainty, ideally we want to quantify as much as possible of it. So, kind of, is it better to be higher up or lower in sense of kind of having high entropy or low entropy?
But better to have low entropy.
Okay. No, I mean, okay, you're right in that. Yes, you're right in that. I mean, in terms of methods comparison, so in kind of in absolute relationships.
High entropy.
Relative, sorry.
Yeah.
High entropy.
Yeah.
Yeah. Okay, exactly. So with this metric, right, with entropy, the way we use it, we want, or we prefer methods that have a higher entropy than methods that have a lower entropy. Obviously, ideally, as you say, we would have a network that is robust to distribution shift. In that case, the entropy would be constant and the test accuracy would be, ideally constant. But obviously, our network is not robust to it. But in this sense, we can quantify distribution shift, right? And that we can say like, oh, I don't know, if you really want, right, you could add some kind of like flag here and say like, okay, my entropy hit a specific threshold. So from now on, like my entropy is so high, I'm going to say my network really doesn't know anything anymore, right? And so maybe now the distribution has shifted so much that we may have to retrain the model or something like that. All right, and we can do the same game for ensembling. So we can also look at how our ensemble method reacts to entropy. So in this case, right, we want to train or we generate an ensemble of 5 neural networks. Why 5? You might think 5 is really low, and it is low. But actually in the original paper, they use 5, and they find that even comparing 5, like an ensemble of 5 members to, I don't know, 50, it doesn't really, like the effect is not that large. And so like the computational cost you save by going small is actually, is outweighs kind of the uncertainty benefit. And so that's interesting. All right, so then we define this, right? And then we train it, right? So in this case, It's not implemented, but we can implement it. Where essentially we just train each of them individually. No rocket science. And then here you have kind of a similar question, right? Is like, do we, right? How do we aggregate over the ensemble members? Do we, again, aggregate over the logits and then run the softmax, or do we directly aggregate over the, yeah. Yeah. You have one more training loop.
13 seconds.
Yeah. All right. And then obviously here now we don't use dropout, right? So we set our networks into evaluation mode again. I mean, in this case, it doesn't change anything because we don't have dropout activated. So it doesn't really matter, but exactly. And then we append our predictions here. Let's see. So in this case, wait, is it that low? Okay.
All right.
Okay. So in this case, actually, our network is surprisingly low. I mean, our ensemble, because you would expect an ensemble to improve actually, but okay. And now we do the same, right? For the rotated images. So we collect the predictions, right? Average them and send it through the softmax. Whoop. Yes. And now we can look at the plot here. I mean, it's already there. All right, and now how would you interpret this plot? Why would you say that?
Because you drop in accuracy faster than the other ones, so it's kind of hard to see.
Yeah, I see what you mean. You mean like, for example, here?
Yeah.
Yeah.
But in general, it's even more uncertainty.
Yeah, so exactly. So the kind of the diversity you have in your ensemble members is larger than the one you would have, for example, in your dropout members. And so you would have even more disagreement, which reflects in even more uncertainty, which is reflected in even more predictive entropy. I mean, this kind of reasoning is a bit simplistic, maybe, to say like, oh, more entropy is better, right? We want more entropy. It's like, okay, I mean, you also want your model to, right, be uncertain in the places where it matters, and like, right, be not uncertain in places where you have a lot of data and things like that. So just saying like more entropy is better, right, is not necessarily true, but in our case, it's true in the sense that as we increase the rotation angle and we increase the distribution shift, we want our model as quickly as possible to essentially, right, detect this kind of shift. And so we want these curves to be kind of as steep and fast up as possible, because we, right, in terms of kind of computational savings or costs or risk even, right, we want to detect the distribution shift as early as possible, right? Because so then once we have a distribution shift, right, I mean, if the accuracy is down here and that's when we start noticing something's wrong, then it's too late already, right? So we want to kind of catch it early. So that's kind of the motivation here. All right. And now just for kind of comparison's sake, right, and we run an actual Bayesian neural network where we actually impose distributions over weights using Pyro. And I think in this case, right, so they suggest we use the first tutorial. yeah, I'll not go through the pyro details, right? But we'll use the tan-h activation function. So we can turn this off. And we will use, again, 3 hidden layers, all 3 layers, all of them linear and fully connected. I mean, linear as in fully connected. So we go from in to hidden, then we have 2 hidden dimensions, and then we have the output dimension. And then we obviously need to implement the forward pass through our model. Right, so we run it through each of the layers and then through the activation function. Again, tan-h activation function, no dropout, no residual connections. So we're done here, right? And then this will give us the logits. I mean, there's no softmax here yet. All right, so we can define our network here. Nothing special here. We can just double check on the names, right? So that seems fine. And now it's like the whole probabilistic definition. So I'm not myself like super familiar with Pyro, but essentially, right, you have this kind of specifying priors on your weights in this Pyro framework, right? And then you have this lift module, which simulates sampling, the sampling procedure from your priors, which you need for a variational inference objective. And then you have this this guide function here that kind of simulates like the whole inference process. But I'll just copy all of this stuff here. Oh, for the sake of time. But essentially what we do, right? In this case, for example, we cheat, as they say, a little. We only implement the final layer to be Bayesian. So what we do, right? We define a normal distribution, right, on the weights and the biases as our priors. So out W prior and here, right? And then we generate, we kind of specify this lift module, which is to generate the samples from our prior. And then we specify kind of our output model, right? So we sample, we do the Bayesian inference step, we obtain, right, run it through the model, obviously now with Bayesian kind of inference attached to it, then run our prediction through the softmax, right? And then, yeah, since we only have 10 classes, right, this is modeled as a categorical distribution. So we have a finite 10 class distribution. All right. So then I implement the guide. Oh, shit. Right. So now these are the parameters in our Bayesian inference step that we actually want to learn, right? So this is what our Bayesian inference does, right? We want to learn the mean and the variance of our outputs of each of our priors, right? So we have these we impose normal distributions on the weights, and now we want to learn the mean and the variance for each of those using variational inference. Why do I say variational inference? Because here it says use stochastic variational inference. And so kind of once you specify these lift and guide modules, the training itself is super easy, right? We specify, we just want to use variational inference, or you could also use Monte Carlo sampling or different, whatever is implemented there. And we define here that our, right, our objective function, our training objective is the elbow. And so in this case, it's the trace elbow, where like you simplify one of the terms by just taking the trace of the matrix, which makes computation faster. Okay, so we specified the objective, and now we can do basically the Bayesian training step. So if you really want to figure out more about Pyro, I motivate you, or I mean, you attended last week, but even that is perhaps a bit very dense, right? I mean, it takes a bit of time to like understand how like this Bayesian theory is implemented in practice, in actual code. Because like in theory, you'd think like, oh, you know, like distributions, how do you encode that? I mean, practically, right? But then you saw perhaps like they use the elbow, which uses the reparametrization trick. And essentially at the end of the day, you're sampling from a standard normal Gaussian and then doing this, all these tricks essentially to transform it into a sample from your, from a Bayesian inference. All right, so this takes a bit longer because obviously Bayesian inference takes always longer, which is one of the big drawbacks of it. It's not scalable. I mean, even in our little toy example, right? If you compare it just in terms of how long it takes to train to like a single model. And the problem is that, I mean, this is one of the key problems of Bayesian inference is like, okay, if we look at a big ResNet or whatever, like try to be Bayesian about it, like you'll be stuck forever. So, or it will not fit in memory or whatever. So that's why also in Bayesian inference, like these other approaches, which are motivated as approximate Bayesian, is one way to go about it. But even within Bayesian inference communities or the community, there's a lot of different ways to run it, right? So in this case, we're even just doing last layer Bayesian, right? I mean, we're not even using all Bayesian weights, right? And it still takes a long time. And so like people have been saying like, okay, let's do first layer only Bayesian, last layer only Bayesian. Let's take a sub-network of the whole architecture and just do Bayesian on that, right? Or kind of like in the same way as like people have been ensembling over everything, people have also been trying to like be Bayesian about different stuff. So I mean, there's work in there, but yeah. All right, so we trained it. And now we will run our prediction. So in this case, we will take 10 samples of our posterior, right, our approximate posterior, and basically average over those. All right, test accuracy is definitely okay. And now for the MNIST rotations, we'll actually look at, 50 samples now. And then we can visualize this. Oh no, wait. That's the worst. Yes. So again, this is these kind of plots is just you just plot the same values. All right, and now we see the Bayesian neural network in yellow, which is also in there. How does it compare to the others?
Almost same as
Yeah. Yeah, and so yeah, and so in terms of just purely quantifying the shift using entropy, which one would you pick? Yeah, I would probably also pick that one. And so, yeah, it's a shame because you'd expect maybe the Bayesian neural network to do better because like you invest more compute into it, but it doesn't. But then in other scenarios, right, it might do better. Or if we do it fully Bayesian, but then it would take a bit longer. All right. But I mean, what do you conclude from that these methods are able to detect the distribution shift or? Yeah. Okay. Yeah. I'd say so. Yeah. I mean, this is similar, for example, to this paper here, right? Where you have so in this case, actually, it's an interesting paper. Just a short intuition, right? So I was saying about going Bayesian. So in this case, right, they go Bayesian on only a subset of the weights, right? And then they use deterministic weights on the others, right? So there's like another way, again, for computational cost. And so I think kind of the experiments we did here are a bit similar in this, right? They increase rotation angles and they measure kind of, so error obviously in our case would be the accuracy. And then here they measure the log likelihood, which is another measure of uncertainty. And you want this to basically go down as you're more uncertain. And so the same way that our entropy went up, right, their log likelihood went down. So I say these experiments here are similar to what we just saw. Although in their case, I guess, yeah, their method is, yeah. All right. So now, final section is on conformal prediction. So now the question is like, okay, could we also use conformal prediction to kind of achieve a similar goal? Like, could we detect distribution shift using conformal prediction? And again, like in conformal prediction, right, you don't really use things like entropy or log likelihood and things like that. So the metrics that the conformal prediction uses is essentially coverage, which is, as we saw before, like that probability statement, right? So like, obviously this is a theoretical statement. How does it translate in practice, right? So in practice, you actually have test samples, and then you actually count like how many of my test samples are inside, you know, like 1, 2, 3, 4. So that's your empirical coverage. And then the second one is set size, right? So you're looking at how large are the prediction sets. And intuitively, you would expect that if your model becomes more uncertain, right, the size of your prediction set or interval or whatever increases, and your empirical coverage would go down. Oh, I just revealed the, sorry. I just revealed the question. So yes, so say again, so what would happen with the metrics? One each. So what would happen with empirical coverage? Go up?
Go down.
Did you listen? Go down? So if I increase rotation angle, I increase distribution shift, would you expect your method to cover the ground truth more often or less often? So it would go down.
Yeah.
And what about the size of your interval? Okay. Yeah. All right. Good. Okay, and in this case, obviously now we're looking at classification, right? So now why do I say prediction set? Because obviously now we don't have intervals, right? I mean, we have 10 labels, right? 0, 1, 0 to 10, or 0 to 9 rather. And now we want to generate some kind of prediction interval, right? But obviously an interval works for regression, but not for classification. So here we use sets. So what conformal prediction will give us is, you give me a rotated image, and I will give you a set. So I will say, oh, this image is either a 0, a 1, or a 5. And I will have this probability guarantee that the true label of this image, which say it's a 5, is inside my set. So it's included in the values that I give you. So again, pretty powerful. You can also use it for sets, right? So let's see if we can capture a similar kind of interpretation. So what I do first, obviously, again, I need to get my calibration data. So in this case, I take the training images and I split 5,000 of these images and use them for calibration. So I take my model, I train it on the training images without the 5,000, right? The 5,000 I use for calibration. So I only train it on the 55,000 training images, but not on the full 60,000 images. All right, let's see. So I'm training a single neural network, no Bayesian, no nothing, just a regular network. Hopefully it trains. I don't know what happened, but we'll take it. All right, so I'm just training a regular network, and then I can double check that the accuracy, even when removing 5K images, right, is similar to what we had before. So obviously I don't want to hurt performance in general by removing images, but I really do need those special calibration images. So you really need this specific calibration set, and your model should not, like, it should be treated almost like a test set. All right, so let's see. All right, I mean, this is the same 94% we had before, so that's fine. All right, and so now in this section, we look at 3 different ways to compute these scores. If you remember in the first example, it was just like prediction minus, absolute deviation between prediction and ground truth. And so for classification, now you have to work with these softmaxes, right? And you have to use these kind of softmaxes somehow to specify how, like, your predictions relate to your ground truths on this calibration data. And so there's no real, there's no single answer to this. So there's 3 methods. Oh, somebody really wants to get in, huh? There's 3 methods from 3 different papers that I wrote down in here, which is naive softmax, adaptive sets, a regularization of adaptive sets. So this is from last year, right? So super recent. And yeah, I think I'm not going to go into like too much detail on this theory because it might get a bit boring, but I strongly suggest, if you're actually interested in this framework, to check this paper here. And if you're interested in uncertainty, you should be interested in this framework, because right now this is the hot topic, at least in distribution-free uncertainty. Like if you really reject all the kind of Bayesian framework and everything that comes with it, right? And then this is your go-to alternative at the moment, because it's purely frequentist, it's purely empirical, it gives you a theoretical guarantee, which Bayesian does not. I mean, I guess you could build credible sets, and it's very simple, right, to do. You don't need to train your Bayesian network or anything. You just, okay, this is not showing. All right. So we'll look at these 3 methods, right? So first off, do the classic 3-4 lines of code that we need here, right? Still recording? Okay. Okay, I think we're back. Sorry. So here, right, this is exactly the formula we had written before, right? You just compute a quantile, right? You compute a specific value and then you just take the quantile. Okay, fair enough. Then we calculate, this is our metrics, right? The mean set size.
Maybe the person who's making all that noise smashed me.
Yeah. I was recording. Okay, okay. All right, we're back. We're back. All right, so we define our metrics. Okay, first, naive softmax method. Again, remember, the only thing these 3 methods differ in is how to compute this agreement between ground truths and predictions. And surprisingly, it makes a huge difference in kind of what you actually observe. So in this first case, all we do is, like, we take 1 minus the softmax of the true label. So we have our model predict for a given image on the calibration data, right? And the model will predict, I don't know, say a 6, even though the true ground label is a 9. And then all we do is now we take 1 minus the softmax the model gave the 9, right? And so intuitively, right, if the model is correct, then that softmax will be super high, then the value will be small. If the model is not correct, right, that value might be large. All right, and so then we use we compute these scores, and then we do the whole thing quantile. And then how do we generate our prediction sets, right? You might ask, okay, in the regression case, we constructed an interval plus minus q. So in this case, all we do, we use this value as a threshold. So for any future test prediction, right, your model gives you 10 softmax scores. And now you say, okay, any softmax score above the threshold, that will be included in my prediction set. And that will be the set of labels I give you, like 0, 3, and 5, or whatever. All right, so we can calculate it. So this is just computing the scores and computing the cutoff, right? So in this case, the cutoff would be 85%. So any softmax value above 85 will be included in my prediction set. And now I need to specify the prediction set, right? So how do I do this? It's a one line, right? Any value above 1 minus q gets included. All right, so now we can have a look. All right, so we see that we wanted 90% coverage, and empirically on the test data, we get 87%. So it's quite close, but it's not quite what we want. And what's kind of weird is like the average set size is below 1. So it's like what does that even mean, right? So it's like on average, your model will actually give you less than, so our conformal framework will give you either 1 or 0. I mean, it might also give higher, but on average, it will give you almost less than 1. And now you're like, okay, that makes 0 sense. And well, it's true that it doesn't make sense in the sense that you don't really want empty sets, at least not in our case. And so there's ways to kind of take care this doesn't happen. I didn't do it here because it becomes a bit technical. But I'd say like on average, right, our conformal framework doesn't really add much in the sense that our model is super certain already about every value, right? So it will always give a lot of softmax to one value. And so a lot of times your prediction set will just be one value. And so almost in a way, you get the guarantee for free because your model's already doing super well. And so we can visualize this here, for example, right? So we have a 7, the model predicts a 7, and then the actual prediction set is only a 7, right? And we can change to a different image, random image, right? So in this case, the actual prediction set is only a 0. But then if we look at this one, it's a 4. And if we look at this one now, right? So here, for example, it's an empty set. So here it's like, the model was a bit unsure, and then like kind of all these softmaxes were not high enough. And so like it turns out to be an empty set. And so in some cases, people actually use this kind of empty set definition for outlier detection. But in our case, we don't really want these empty sets, but I just didn't include the way to handle them for this case. Then remember, this is the naive softmax method, right? So it's not the one I would suggest for you to use. This is the basic one. All right. And so now, obviously, what can we do, right? We can do a similar thing. We can take our rotated images and we can basically evaluate on the rotational images and always use the same kind of information we got from the calibration data to inform our set sizes. I'll be done in 10 minutes, don't worry. Got the time, right? And so then we get something like this. So how would you interpret this? So in specifically the two metrics we have, right, is the mean set size and the empirical coverage. And remember, we said at the beginning that we want coverage to go down and we want set size to go up. So in this case, set size actually goes down a little bit and it kind of stabilizes again.
So it returns more empty sets.
Yes, exactly. Exactly. That's a good, and that's very good because this is somewhat counterintuitive. You wouldn't expect this to happen, but in this specific case, exactly. So as the model becomes more uncertain, in fact, right, we have more empty sets. And so the actual mean set size decreases. So that, yeah, good catch. So, but we'll see now that in the two following methods, which are a little more sophisticated, actually we can kind of counter this effect here. But this was, yeah, it's kind of like a bit like a trick question. No, it's good. It's good. Yeah, good. Okay, and so now in these two following methods, I'll not go to the details too much, but essentially what we do is instead of just looking at the softmax of the true class, we now consider the softmaxes of all the other classes as well. So in a way, it's kind of like you encode more information in your conformal scores, which downstream helps you to make better prediction sets. So I mean, here are the details, but yeah, let's not look at that specifically. But in a way, we're using a different kind of score, right? And actually, hopefully, a better one because it's not the naive method. All right, so I'll just replace the prediction set here. And now we see these values look a little bit better, right? We wanted 90%. This method actually gives us 92% coverage, which is nice. Anything above 90 is good. And we have a mean set size of 3.2. So on average, right, our prediction sets will include 3 values. And so we can look at this one, but still we could also generate empty sets. This has not been tackled here. So here we only have a single value. This one, for example, the model is quite unsure a little bit, right? At least in terms of softmax. And so your prediction set actually includes 2, 4, 8, and 9.
Maybe I missed it, but are those predictions ordered in, or do they just happen to be increasing, or are those in order of confidence at all?
Yeah, exactly.
Literally a set.
Oh no, this is literally a set. Yeah, so it doesn't have to be ordered. No.
You could order it also, right? Because they still have a softmax.
Yeah, exactly. Yeah, you can. I mean, this is just so these are actually. So this is where the guarantee is now, right? So now, for any test sample in the future, right? I mean, we see it here even for all the test MNIST data, right? I can guarantee you with even more than 90% that all these sets always include the true value. So in this case, it would be a 4. So the 4 is actually in there.
Yeah.
And so for over 90% of the test data points, our sets here, they include the true value. And this is the guarantee that conformal can give. All right, and now we can do the same game again on, or I don't, let's not run the code because it's the same, but we can run the same game. And now we see this behavior here. Yeah, exactly. And interestingly, the coverage doesn't necessarily decrease quite as much, which is actually nice to see because it shows in a way that like your model is adaptive in that like it reacts by largely increasing the set size, right? But then because the set sizes are so large, right, the coverage doesn't necessarily I mean, it still degrades, it's still below what you want, right? But it decreases less, which is
so somehow it doesn't get over 6.
Yeah. I'm not. No, I don't think so. It's just, I guess, in a way, like you only have 10 classes, right? You only have 10 classes, and so perhaps if your threshold Q, right, in order to kind of have enough softmax mass distributed to pass that threshold, right? If you distribute it maybe to 10, then each one of them is just too low, right? So it's kind of like. So it kind of stabilizes at these 6. But then again, if you have 10 classes and I give you 6 of them and I say, oh, the value is somewhere in there, it's not very useful, right? I mean, it's like.
I gotta catch my train.
Oh, yeah, no worries. Yeah, and then this one is the last method.
Thank you.
Yeah, no worries.
Bye.
You almost made it. Take care. And so now this one, right, we say like, okay, actually, if you have a set size of 6 for 10 classes, like it's not very useful, right? If you give me an image and you say like, oh, I want a guaranteed prediction set, and I say like, oh, it could be 0, 1, 2, 3, 4, 5, 6. It's like, okay, thanks, but like, what do I do with this, right? Oh yeah. And so in this case, right, this paper basically added a regularization term to improve kind of set size. So we can run the whole game here, right? We get the same kind of ideas, but now what's really nice to see is the coverage is first of all, it's closer to 90, which is good. So you don't overcover, and your set size is much smaller.
Why is overcovering?
So overcovering per se is not bad, but overcovering often comes with a loss in performance. Yeah, exactly. So yeah, exactly. So often, like even just adding a 1 or 2%, like, and then your set size blows up. So you really want to be as tight as possible to those 90% that you actually expect. So in this case, kind of these being slightly below, this is kind of more based on like empirical stuff. So this is definitely like a good coverage.
Yeah.
And then it's nice to see that the set size is almost 1, right? So it's like I can almost guarantee you, by only giving you single or maybe 2 values or so, I can guarantee you that like the true value is there.
Does this one also theoretically return empty sets? Or...
Yeah, this one cannot. Yeah.
So you can
Yeah. So I didn't address empty sets in this example, just because it adds a bit of complication. And perhaps because you want to use empty sets as some kind of signal for outliers or whatever. All right, and then we can run the same game here, right? And again, we see, in this case, coverage actually decreases more rapidly. So in a sense, the previous method was a bit more robust, but obviously the set size now is kind of much smaller, right? So even if I rotate the images so bad that, right, the model has never seen that stuff before, and still the set sizes are like 2. So it's like, it's really nice to see, but it's also good to see that the trends, the behavior you have, right, is what you'd expect.
as there's more discrepancy between the test and training.
Yeah, exactly. And in this case, particularly between the calibration and test data. Yeah, and then, so what will you conclude from that? Like, could you also use conformal to detect distribution shift, or?
Yes. Because when you see the set size go up, this way that we'll see a bunch of these clearly the method is uncertain at that point.
Exactly, yeah. So yeah, exactly. Or like a combination of the two.
Yeah.
Yeah, and so I think what's cool to see is like these are like Bayesian methods, and it's based on predictive uncertainty and all that. And then here in conformal prediction, you have a completely different framework. You use different metrics. You're based on statistics and all that. And still you can recover the same kind of signal and information with both of these approaches. And so it goes to show that in terms of uncertainty, right, there's many ways to quantify uncertainty. And I think one of the key challenges, because there is no ground truth, right? It's like, is this uncertainty correct or not, right? You don't know because, yeah, again, there's nothing, right? It's like, so I mean, these kind of experiments, you expect uncertainty, right? And so this is kind of like your signal, but you don't know. It's a really difficult problem, but it's cool to see that you can approach this problem from very different directions, and you can still kind of get the same info. So yeah, that's the second tutorial. So you got to see a deterministic neural network, an ensemble neural network, and deep ensembles, Monte Carlo dropout, conformal prediction, and the Bayesian network, both for a 1D regression toy example, and then for an actual MNIST classification task to detect the distribution shift. And they do it to different extents, and then, right, how to use it downstream is another thing, but like they're able to do it. So yeah. Thank you very much for attending in person, and yeah, hope you have a good day. Bye-bye. Sorry, this is just for